Okay, so we'll continue with properties of integration and how to change the limits and integrals as we have seen in the case of monotone convergence theorem and Fathou's lemma. Before we go ahead, let us just extend one of the results we had earlier. So let us recall the following result. If so, always we will have x f mu, where x is a space, f is a sigma algebra, mu is a countably additive measure. If we had a simple function 0 infinity simple measurable function, then we know how to define a measure, right. Nu a was defined to be a s d mu and nu was a measure. Now with the help of monotone convergence theorem, we can generalize this result. We do not need a simple function, we can change that to any positive measurable function. So let me state this as a theorem. So I have x f mu and f is a positive function from x to 0 infinity, measurable of course. Okay. Then the assignment nu, so I am using the same notation, nu a equal to integral over a f d mu defines a measure on script. So we have of course seen this for simple functions, we just need to do it for all positive measurable functions. So well, this is, so first property is of course always trivial, this is 0 because mu of why is this? So this is because mu of the set phi is 0, and so if you integrate over a set of measure 0 you will get 0. This was one of the properties we looked at earlier. Second one is the countable additivity. Okay. So we take disjoint sets A1, A2, A3 etc. disjoint, and let us say union Aj, j equal to 1 to infinity equal to A. Okay. So Aj are disjoint, so because of that, so Aj are disjoint. So because of that, if I look at indicator of A, this is simply summation indicator of Aj, right, j equal to 1 to infinity. Why is that? At any point chi A is 1 or 0. Chi A is 1 if x is in A. X is in A would mean that x will be in one of the Aj's, and so this will be 1. But they are disjoint. So if it is in one of the Aj's, it cannot be in other Aj's. So that is why these two are equal. Okay. So because of this, if I look at nu of A, so remember the definition, this is the definition, nu of A is integral over A f d mu, which of course is integral chi A times f d mu, right, that is the definition. But chi A is the sum, so I can write this as in summation j equal to 1 to infinity chi Aj times f d mu. But now you are in the previous case where you are adding up positive measurable functions and integrating. So you know that summation comes outside. So this is summation j equal to 1 to infinity integral over x chi Aj times f d mu, which is summation j equal to 1 to infinity integral over Aj f d mu, and this is the definition of nu Aj. So what did we prove? We just proved that nu of A is equal to summation j equal to 1 to infinity nu of Aj, right, if Aj are disjoint, and so Aj, so nu is a measure. So we have proved that this assignment defines a measure even if f is a positive measurable functions. not just for simple functions, we have it true for positive measurable functions. Okay, so now we go ahead. So let's just recall that we started with simple functions positive, then we defined x t mu, right. So this was summation alpha j mu e j equal to 1 to infinity, sorry, j equal to 1 to n, where S had the expression summation alpha j chi e j. Then we looked at measurable f positive, and the integral was defined to be the supremum over all simple functions less than or equal to f x f d mu s d mu. Now, so this defines integration for, so this is for positive functions, integration for positive measurable functions. Now we want to define it for real valued functions. So we will extend this to real valued functions and complex valued functions and complex valued functions. Okay. Well, how will we do that? So let's stick to real valued first, so that it's, so let me define things here. Suppose I have a measurable function taking values in r. It can take values in minus infinity plus infinity also. Okay. So it's possible that it takes values infinity and minus infinity. We will assume it's a measurable function, and I am looking at the integral of f. That is what I want to define. So let us define two quantities f plus. F plus at x is maximum of f of x and 0. Okay. F minus x is maximum of minus f of x and 0. Okay, so this is called the positive part of f, this is the negative part of f. So notice that both of them are positive functions, measurable. Okay. Well, what is the relation between f and f plus? Well, f of x at any point is simply f plus x minus f minus x. Okay. So let's try to understand this. Okay. So let us say I have f sort of drawn here, something like this. This is my f. What is f plus? F plus is the maximum of f and 0. So wherever f is greater than or equal to 0, that would be your f plus. Right. So let's see this part. Okay, maybe I'll take black. Okay. So this part will give me, okay, this part gives me f plus. Well, up to here, right. In this region, the region after this, f has negative values. So maximum of f and 0 will be 0. So f plus will be like this, and then it's like this, then it is like this, and so on. Okay. What would be f minus? Well, f minus is going to be, well, f minus here would be 0. Now in this region f is negative. So I look at minus of f, so it would be something like this. So this is minus f, and I am looking at the maximum of minus f and 0. So that will give me this part to be to be f minus, okay, and f minus will be 0 here. So, wherever f plus is positive, f minus will be 0, and wherever f minus is positive, f plus will be 0. So, all you are doing is you are wherever f is positive you keep it as it is, wherever f is negative you reflect it, right, that is your f minus. This is f minus and this is the f plus. Okay. And so, if you look at these two, you will see that f x is simply f plus x minus f minus x for every x in x. Of course, only one of them is non-zero. Now, that allows me to define the integral, right. So, let's start from here. So, I have a measure space, I have f from x to r, or I can include minus infinity to infinity, measurable. I can write f of x to be f plus minus f minus. The advantage is f plus and f minus are positive measurable functions, and for this I know how integrals are defined, that we have already done. This and integral of f minus x's, and the integral is supposed to be linear. So, if I integrate f, I should get the difference of these two, right. So, that is one way of defining. So, define integral over f d mu equal to integral over x f plus d mu. I know this is well defined, minus integral over x f minus d mu. Now, the problem is this could be infinity, both of them could be infinity. So, we will avoid infinity minus infinity situation. Okay. So, for all practical purposes we can assume that these two are finite. Okay. It still makes sense if one of them is infinity and the other is finite, because you will either get positive infinity or minus infinity, but that is not, we do not have to really consider such situation. So, we will consider functions with the property that both f plus and f minus are finite integral functions. Integrals of both f plus and f minus are finite. Okay. So, we will put this in a more general framework. So, now let us look at complex valued functions, just to extend this to complex valued functions. F going from x to the complex plane. Of course, it can take values infinity and so on. Let us again not bother too much about it. I can write f of x to be equal to u of x plus I times v of x, okay, where u is the, so u will be the real part of f, u is the real part of f and v is the imaginary part of f, right. At each x we are looking at u and v. So, if this is measurable, then both u and v are measurable. Okay. Why is that? Well, you can look at the map. So, I have f going from x to c, and I have from c to the real line I can take the real part. Okay. This is a continuous map, right, call that capital phi. Then I am looking at capital phi composed with f, right. So, this would be x to r, and that is f that is x going to u of x, and so this would be measurable, right, because this is continuous. So, we have seen that. So, both u and v are measurable real valued functions, real valued functions. So, if their integrals are finite, as we have seen earlier, if I have a real valued function, I know how to define the integral, right. So, I know how to define the integral for u and v. So, those integrals make sense, that means they are finite, I can define the integral of x. So, this take this as a definition, define f d mu to be equal to, of course, you want it to be linear with respect to constant. So, f is written as u plus I v, right. So, one should have the definition to be u d mu plus integral I times integral over x v d mu. This would be the definition. Well, how is this defined? Recall that this is integral over x u plus d mu minus integral over x u minus d mu plus I times integral over x v plus d mu minus integral over x v minus d mu, right. This is how it will be defined. Of course, some of them may be infinity and things like that. So, to avoid such situation, we will restrict ourselves to the following class of functions. Okay. So, let's define this. So, to avoid infinity minus infinity situation, we only consider the space, we consider the space of functions L1. So, the significance of this notation will be clear later on. So, L1 I will denote this by x f mu. Sometimes x and f are clear. So, we will simply look at L1 of mu. Well, what is this? This is the collection of complex valued measurable functions, complex valued measurable functions such that integral over x mod f d mu is finite. So, remember if f is measurable, then so is mod f, right. Mod f, why is that? Well, because f goes from x to c and the modulus function goes from this to 0 infinity, right. And this is a continuous function and we are composing these two. So, this is measurable, and so this integral would make sense, that integral over x mod f will make sense. And now this is a positive function, so it is either infinity or a finite number. So, if it is finite, we say f is in L1. Okay. So, we say f belongs to L1 of mu if integral over x mod f d mu is finite. Well, in that case, so let us look at mod f. So, what is mod f? So, if f is real valued, I know that f is f plus minus f minus. What is mod f? Mod f is the sum of these two plus f minus. So, if mod f has finite integral, this would imply that both of them are finite. This is finite and integral over x f minus d mu is finite. So, this would make sense. Integral over x f minus d mu makes sense, because there is no infinity minus infinity situation. Okay. Similarly, if f is complex valued, so you write f as u plus iv. I know that mod u will be less than or equal to mod f, because that is the real part. Similarly, mod v is less than or equal to mod f. All these are measurable functions. So if I look at mod f has finite integral, then this will tell me that both mod u and mod v have finite integrals, right. So because of that and whatever we have just discussed, it follows that this complex number plus I times integral over x v d mu, this is the integral of f, right. This makes sense. So when we look at functions in L1, so if you look at functions in L1, then all the components will have finite integrals. So everything will make sense. So this is the space we will work with. Okay. So let's conclude with a easy theorem which will complete the linearity properties of integrals. Okay. So I take f g in L1 mu. So remember L1 mu, there is a space x, there is a sigma algebra and there is a measure, right. And this is the collection of measurable functions whose modulus have finite integral, right. That is the set we are looking at. So I am looking at f and g in L1 mu and some constant in complex plane, then we have the full linearity of the integral. What does that mean? Integral over x alpha f plus g d mu. Remember all this makes sense, equal to alpha times integral over x f d mu. Alpha is a constant, so that has to come out. Remember alpha is a complex number. We have done this for positive functions and positive numbers. Now it is true for all real number or complex numbers and complex valued functions, plus integral over x g d mu. Okay. Well, how would one prove this? So I will not get into the full details. So let me give you sketch of the proof. So first of all, enough to show that if I have alpha a complex number, then that comes out from one integral, right. And you can also add integrals. If I take two functions, I know this already for positive functions, but it is true for complex valued functions is what one has to prove. F d mu plus integral over x g d mu, right, so that it is linear. Well, how does one prove this? So let me give you a sketch of this sketch of the proofs. So let us keep some, yeah. So first assume f is real valued. First assume that for positive functions we already know. So if f and g are positive and alpha is positive, then this is something we already know. So first assume that f and g are real valued. Okay. Then I know that f can be written as f plus minus f minus, g can be written as g plus minus g minus. So remember all these functions are in L1, so their integrals are all finite. So we don't need to worry too much about infinity minus infinity situations, it does not happen. And let us take h to be f plus g. Okay. Alright, so f plus g I can write as f plus g plus minus f minus plus g minus, right. Okay. I can write h also as, so h I can write as h, well h can be written as h plus minus h minus, right. This is true for all functions. So I have two expressions for h, one is this and one is this. So they have to be equal. So h plus minus h minus is equal to f plus g plus minus f minus plus g minus. So, this is a simple manipulation which will give us the result easily. So, we bring certain things this to the left hand side and h minus to the other side. We are going to get h plus f minus plus g minus, this is equal to f plus g plus h minus. Okay. So, this went to the other side and this came to this side, that is all I said. Well, what is the advantage? Advantage now is that everything is positive. So, both sides have positive functions, positive measurable functions, right, and all finite integrals, and all of them have finite integrals, finite integrals. Why is that? Because they come from L1. So, all of them will have finite integrals, they are positive, and for positive functions we have linearity, right. So, this would imply integral over x h plus d mu plus integral over x f minus d mu plus integral over x g minus d mu equal to the integral on the right side. So, again that gets distributed because of linearity for positive functions which we already know, plus integral over x h minus d mu. So, now what remains is to simply rewrite it, right. I can bring this. So, take this to left side LHS and take this whole thing, right, that is what we did earlier, this to the right side, take this to RHS. So, if I bring this portion to the left side, so I will have integral over h x h plus d mu minus integral over x h minus d mu, right. But this is the definition of the integral for h. So, this is simply integral over x h d mu, h is simply f plus g. So, I have f plus g d mu on the left hand side. Well, what do I have on the right hand side? So, I have taken this to the right hand side. So, I distribute accordingly. So, I have integral over x f plus d mu. So, that is this term minus integral over x f minus d mu, that is this term, plus integral over x g plus d mu, that is this term, and the other term which was brought to the right hand side g minus d mu, that is this term, okay, which is, I know this, what is this, I know what is this, right. So, this is simply integral over x f d mu plus integral over x g d mu. So, what we have proved is if f and g are real valued functions, then the integrals add up, right. Integral of f plus g d mu is same as integral of f plus integral of g. Now, you continue this. So, I will not bother too much about the proofs now. You continue from this point. So, next step prove that integral over x minus f d mu equal to minus integral over x f d mu. Well, how will you do that? That is not difficult because you know how f is. So, if f is like this, you know how minus f will be. So, write minus f, okay, and find out the relation between, well, this is actually straightforward. F I can write as f plus minus f minus. So, what will be minus f? Minus f will be f minus f plus, okay. In other words, the positive part of minus f is the negative part of f and negative part of minus f is the positive part of f. Okay. And so from here we know that integral over x minus f d mu, well, what would be that? Use the positive part and the negative part, right. So you will get integral over x f minus d mu minus integral over x f plus d mu, which is simply minus of integral of f, right. So that is trivial. So minus 1 comes out. Now if I have alpha in the real line and f is a real valued measurable function, so let us take two cases, alpha positive and alpha negative. If alpha is positive, well, how will you write alpha into f plus minus f minus? This would be alpha f plus minus alpha f minus, and this is the positive part because alpha is positive part, this is the negative part, and you know how the integrals are, and alpha will come out because it is positive, right. If alpha is negative, what will happen? Alpha into f plus minus alpha into f minus, you will have to write as alpha is negative. So I can write this as minus beta, where beta is positive. So this would be beta into f minus minus beta into f plus. So this is the positive part, this is the negative part of the function, and so integrals will get distributed, beta will come out, which is same as alpha coming out. Okay. So that this proves everything for real valued functions. Real valued functions. Well, how will you extend it to complex valued functions? So for complex valued functions, the proof is same. Yeah, 2 minutes. For complex valued functions, proof is same. Proof is same. First check that integral over x I times f d mu equal to I times integral x f d mu, okay, where I is the constant, right. I is such that I square is minus 1, and then using the previous properties you can extend it to all complex numbers alpha. Okay. So we will stop with this. What we have proved so far is that we are starting from positive measurable functions, defining their integral. We have extended the definition of the integral to real valued functions first, taking the positive part of the function and the negative part of the function, and then we have gone to complex valued measurable functions. So we restricted ourselves to functions whose integral is finite, so that there is no infinity minus infinity situation, and the integral is linear, just like what we have seen for positive functions. We can extend it to complex valued functions, and if you multiply by a complex constant, it comes out, and integral of f plus g will be integral of f plus integral of g. In the next class we will deal more with complex valued functions and prove the next important theorem called Lebesgue's dominated convergence theorem, again which allows us to interchange limits and integrals.